this in a good position? Am I audible but not too audible? All right. So to continue with where I left off last time, in comparison to the previous talk and to a number of the other beautiful talks I've heard here, what I'm going to tell you reminds me of a story I heard about the famous mathematician Stan Coulomb, who was found by a mathematician friend sitting around looking very depressed one day, and the mathematician asked him why, and he said, well, I actually wrote a paper with a number with a decimal point in it. And what I'm going to tell you is on some level in that category. So what I went over last time, rapidly at the end of the talk, was the first and canonical example of a system with intrinsically what you might call correlated electron properties. And what I wanted you to take away from this was four things, only three of which are written on this view graph. We have a, here's the picture, all right. So if you just look at the properties, for example, of helium-3, what you discover is that there's a wide range of parameter space where the reasonably low temperature properties are those of a Fermi liquid, which you should think of, roughly speaking, as a thing which has the properties of a non-interacting electron gas, just with renormalized parameters. And then there are a number of characteristic questions which are beyond the scope of this Fermi liquid theory. In particular, a reasonably well-defined higher temperature range, where the properties look in some sense reasonably simple and regular, but are not those of precisely those of a degenerate quantum gas. Second, this Fermi liquid is unstable to other phases with interesting properties, such as the superfluid A and B phases. And Fermi liquid theory by itself doesn't tell you how that instability works. And the third thing you might want to know is, of course, the values of all of these parameters. Now, the thing which I didn't write here and I didn't emphasize is that, as is essentially obvious, the fermion-fermion interaction in helium-3 is basically a hard sphere interaction. Right? It's just you can't put two helium-3 atoms in the same place. That has no particular long-range character. So all of this stuff really comes from a strong short-range repulsion. Okay. Now, so that's what I said here. And finally, a good thing to look at is the Green's function, which I defined last time, and in particular, the so-called coherent or quasi-particle part, right? And basically, in some sense, these insights, which came from helium-3, are the basis for how we think about correlated electron materials. So now I want to turn to actual materials for a little bit and show you how these ideas play out and introduce one other important idea. Okay, so really what we all do in thinking about basic solid-state physics is conceptually the Fermi liquid approach. We start from some kind of effective non-interacting electron theory, and then we add interactions, which we might like to hope simply renormalize parameters and change things a bit. All right? So that's the same concept as we did in helium. The new feature, of course, in a solid is that there is a potential, periodic if you have a perfect crystal, and not periodic if you have a random crystal or some disorder. All right? So that means you start from a Hamiltonian which looks conceptually sort of like this. The whole construct of modern band theory, which I also discussed last time, says that really if you want to treat the interacting electron gas, you wind up solving a problem like this, but with a slightly more complicated potential here, which depends in some self-consistent way on the density. All right. So we all know what happens when you solve this kind of problem. Because there's a periodic potential, the eigenstates now are energy bands. So the system is periodic in K-space. You have a Brillouin zone, which is the basic periodic unit. Within that zone, you have an infinite number of solutions, which correspond to the energy bands of the solid. So here is an example of energy bands of a solid chosen not actually at random. This is lanthanum titanium 03. Obtained from a density functional calculation here, all right? And what you see, this axis is some trajectory in momentum space through the Brillouin zone. This is energy, and these blue things are the energy bands. All right? And so you see some bands. This solid line here is the chemical potential. We all learned in beginning solid state physics that you have two kinds of solids, which are metals and insulators. In an insulator, all the bands are either empty or full. In a metal, at least one band is partly filled. Okay. So in traditional band theory, therefore, clearly, you would say that it's impossible to get an insulator. Well, because each band can hold two electrons, one is spin up and one is spin down. You would say you cannot get an insulator, at least a paramagnetic insulator, in band theory if the number of electrons per unit cell is not even. And in fact, if you do the electron counting for this material, you will discover that the number of electrons per unit cell is odd. So it's 1, modulo 2. And so you see here that there are some partly filled bands, like this guy, which this part is below the Fermi level, this part is above. And if you were to add up all the electrons in these bands, you would discover that there was 1. Okay, now, this band classification of metals and insulators does not always work. In fact, in this material, the number of electrons per unit cell, as I said, is odd. And yet the material is insulating. This is the optical conductivity. Never mind all the details. What you're supposed to see is this curve here for lanthanum titanate says that the conductivity is 0 below a gap, which is about 2/10 of an eV. So this thing is not a metal, because if it was a metal, the conductivity would be non-zero. This big spike here, by the way, is some kind of phonon. So lanthanum titanate is an insulator when band theory tells you it ought to be a metal. It gets worse if you go to yttrium titanate, which is very much like lanthanum titanate. It's basically the same structure, basically the same bands. The substitution of lanthanum for yttrium for lanthanum doesn't change the electron counting. It changes little details of the crystal structure, like how much the titanium-oxygen-titanium bands are buckled. But you would get a band structure which doesn't look very different from this, and you see that the insulating gap is, this one here is much bigger, it's a volt. So, there are classes of materials where the band classification fails essentially completely. All right? And these things, the jargon name for these things is Mott insulator. There is a very comprehensive review in Reviews of Modern Physics, now a little more than a decade old, which lists essentially all of the known Mott insulators and all of the properties which were known at that time. And it's a very useful resource. Our qualitative understanding of Mott insulating behavior really comes both from Neville Mott, who is shown here, who is unfortunately no longer alive, and John Goodenough, who is at University of Texas and still going strong. So a Mott insulator, basically what you should say is that there are many materials, transition metal oxides such as lanthanum titanate, organic materials with a quasi-two-dimensional electronic structure with names that I can't pronounce, carbon-60 and its variants, etc., which are insulating when band theory says they should be metallic. Now, the common feature of these things is relatively narrow bands, that is, they don't disperse over a wide energy, and relatively well separated from other energy bands. So if you go back to my example of lanthanum titanate here, I've highlighted in green the energy bands near the Fermi surface. They're well separated from these guys here. They're moderately well separated from these guys up here. And the total range over which they go, this energy units is Rydberg's, which is, if I have this right, 13.6 or 27 electron volts, I never remember. But the total bandwidth here is on the ballpark of a 10th or 0.15 Rydberg. So the band is relatively narrow, a volt or something. Right? And this is the common feature of Mott insulators. The other interesting thing is that the spatial extent of the charge in the orbitals we care about is small. So if I go back to here, if I wish to discuss the low energy properties, I might want to focus on electrons in these bands. All right? Now, it turns out to be possible to tease out from the band theory calculation how big is the wave function corresponding to these things. All right? In fact, through a complicated set of circumstances which I don't want to discuss in detail, a particular variant of a band theory calculation for a particular variant of this band structure says that the ground state is a fully polarized ferromagnet. This is almost certainly a wrong prediction of this variant of band theory, but that's what the program gives. Now, if it's a fully polarized ferromagnet, then what you can get out of the band theory is not just the charge density, but the charge density per spin, therefore the spin density. It's very natural to imagine that the ferromagnetism arises from the electrons in these bands, and therefore by plotting the spin density, which is directly given to you from this local density approximation band structure, you can get a reasonably good idea of the density of charge in that band without doing any nonsense. All right, so here's a result of the spin density. You take a unit cell, you integrate over the z direction, and you make a map of the spin density in the xy plane, and you use this false color contour plot business. So what you see is that all the density is concentrated right here in the middle of the unit cell. Right? So the orbitals that you care about are spatially localized on the scale of the interatom distance, which is from here to the next unit cell would be over there.
Sorry, this is a unit cell in real space?
This is the unit cell in real space. This is the charge density in real, well, the spin density, which I interpret of a fully polarized ferromagnetic state, which I interpret as the conduction band charge density.
So how many atoms are in the unit cell? How many?
Lanthanum, titanium, O3, that's 5.
So where are the locations?
So the titanium is here. This is the unit cell in real space, 0, 3.91 is the lattice constant. So you have titanium, you would have an oxygen here, and you can see there's a bit of weak contours, another oxygen here, here, and here. And I've, again, taken this spin density and integrated it, or the unit cell is basically a cube in real space, and I integrated it over the z direction and plotted it as a function of xy. So this is m of xyz integrated in z over the unit cell and plotted versus xy. Right? And again, the point of looking at the magnetization is that that's a good proxy for the conduction band charge density as opposed to the total charge density. Yeah?
So this is a calculation.
This is a calculation.
But on the other hand, you argue this calculation we shouldn't believe from the point of view of insulating versus it's not
That's correct.
Mott insulating.
Correct.
But you're somehow believing this local physics.
Correct. So this is a very good point that Leo raises, and this is I would say, a basic intellectual tension in all of our studies of strongly correlated materials. All right. So this is obtained from a density functional band theory calculation, which is within its approximations supposed to reproduce for you the charge densities and the total energies. So I would therefore argue, and in fact this is from a small generalization of this, in particular to allow for spin polarization. So you can look at the charge density both for spin up and spin down, and this is the difference between those two. And it's also, this is a detail I don't want to go into, this is an LDA plus U band structure, so it's a somewhat ad hoc modification of usual band theory. Right? But if you leave that aside for the moment, the idea is that if you were to have the exact density functional and it were to predict a fully polarized ferromagnetic state, which this thing does, then this would be the spin density, because the whole thing is cooked up to give you the exact density. So it's therefore reasonably plausible that you should believe this as a representation of the density, independent of all the other properties which you're getting wrong. Now, as you'll see as we go on, basically what one does these days in thinking about correlated materials is that you use band theory methods, right? To get not just energies and total densities, but you actually interpret the eigenfunctions, the Coulomb eigenfunctions of your favorite band theory procedure as having some actual meaning for the compound. So basically where I'm going with this is you take not just the density, but the orbitals which give rise to this density, and you say that even though as a matter of principle they have no actual meaning, we're going to assume that they're a reasonable representation of the actual orbitals and the materials, and then we're going to decorate that with some additional interactions. And so if you don't want to believe in the orbitals, then you can forget this whole research program, basically. And another way to put it is that somehow, if you think about it carefully from a many-body physics point of view, in a solid, the idea of a titanium 3D orbital doesn't really have any meaning. It's a single particle quantity in a many-body state. In practice, it seems to have a reasonable correspondence to reality. And exactly how reasonable is still an open question. Now, was there another question over there?
I'm just wondering how come there's no density between
This is where the magnetization is. I mean, there's a very small density. You see some of these contours here, so it goes down and then it goes back up. But that is the spin density which comes out of this calculation. And it's very small on the intervening oxygens.
There's a lot of other density
this
involved
is
in mechanical bonding, but that's a lower.
correct. Well, it's not that it's lower, it's not spin polarized. Remember, this is the magnetization density, which I'm interpreting for you as the conduction band charge density. And the advantage of this calculation, again, is that even though this is almost certainly a wrong prediction, once you have it, it allows a reasonably unambiguous identification of the charge in the conduction band without having to go through this story of fitting all the wave functions and deciding which ones you like and which ones you don't like. Right? This is just the spin density.
The spin density from other bands that are filled.
Yeah,
just
right, so with filled bands wouldn't give you any net spin polarization. So the assumption that goes in here is that the partly filled bands are the thing which is giving you the polarization. And indeed, the polarization within the calculation is 1 spin half per unit cell. All right, and there are a very large number of calculations which show this essential feature, that these guys which exhibit this Mott insulating behavior, what you're really talking about is charges which are degrees of freedom that you care about, which are reasonably localized on the scale of the unit cell. Okay, so implications of this nearly localized wave function are obvious. First, your bandwidth really arises from overlap of orbitals. If the orbitals are very localized, they don't overlap that much, and therefore bandwidths are small. If you like, therefore, the starting structure has a heavy mass or a narrow band. Right, if you go back to here, the reason that these orbitals are confined within this relatively narrow window is because they're spatially localized and don't overlap all that much. Right. The second consequence is that there is a strong hardcore interaction. If you just think in a sort of loose chemical way about trying to put 2 electrons into one of these orbitals, because the orbital is small, the E squared over R energy of putting 2 guys in the orbital is big. Therefore, there is a strong local repulsion, right, which is particular to these small orbitals, and which is rather analogous to the obvious hardcore repulsion that you got in helium-3. So therefore, one would like to believe that this strong local repulsion is the dominant interaction, right? And thinking about it along those lines is what led Mott, Goodenough, and Hubbard, of whom I actually couldn't find a picture, to a model for this kind of physics. All right, and what they said is if you abstract out the orbitals you care about, this one, with this sort of localized shape, eventually the model that describes what electrons in these orbitals are doing is very simple. You have some operators which create electrons in these orbitals, you have some parameter which lets electrons hop from one orbital to another, and you have an energy cost for putting more than one electron on the side. Okay? So that this is sort of a minimal model that would encode the information that I just sketched for you. All right? And,
So,
yes?
so I have heard this statement that it's a minimal model so many times.
Yes.
So, in your experience, all these 35 years or something.
Thank you for making me feel old, but carry on.
I'm saying 35 years that we discuss about
Yes.
this model, I mean, as a community.
Yes.
Do you really believe that's a minimal model? Is it really?
Actually, I think the correct answer to that is both yes and no. Let me go on with that. It is certainly a rich and interesting model which contains a lot of physics which is still not completely understood and which has a non-zero overlap with what's going on in real materials. Now, there's a couple of obvious ways to decorate it, which I'll come to in a moment, which are essential on the level of this minimal model and which bring you physics. And then there are things which are not included in here at all, which are likely to be important and nobody has really thought about. Right? So the answer is that it's a minimal model. It's not orthogonal to the truth, but its overlap with the truth is not one. And whether it's 0.2 or 0.5 is something which we can discuss. Right. And in my view, really, that is one of the, let's say, one of the research frontiers in this business of correlated materials. Right. But notice before we get there, there's an obscurity in here, which is that you really have to believe that these, well, an issue in here, which is that you really have to believe that these orbitals have an independent existence. Right. That you can take from the full set of orbitals in the solid, a few that you're interested in, treat the orbitals as real, and just decorate it with some interaction. Right? And that is the approach that everybody has followed. Mostly because it's, doing something is better than doing nothing, and this is what one knows how to do. But there are obvious questions. Okay, so the important parameters in this. There's a relative interaction strength, loosely written U over T, but the strength of this repulsion is compared to the bandwidth. Right? And then there's a density of electrons N. All right, so now let me give you a qualitative view of the physics of this thing. All right, and this will be entirely a pictorial discussion. All right, so you have a conventional band insulator. The physics really is of filled shells. Right, so you got 2 electrons on each site. Pauli principle says nobody can move. You got an insulator. You add a hole. Now that can move, it's not blocked, so you get a conductor. Okay. You can describe this in momentum space. What you get are filled and empty bands with a gap between them. If the gap is there and you fill up one of the bands, then you get an insulator. All right. So now let's ask what happens in this Hubbard model. Then the physics is a little different. And the jargon term I think one should use is Coulomb blockade. If you start with a site with 1 electron on it, if the repulsive interaction is strong enough, you don't want to put a second one. So if you're in this situation, you have a strong repulsion, then in some sense no charge motion is possible and you can get an insulator. Right? And that was really the insight of Mott back in the mid-50s, more or less. Now, this insulator, unlike the band insulator, is not entirely inert. Unless the repulsive interaction is infinite, you can imagine a virtual process. Right? It may be small if the repulsion is large, but you have a hopping which mixes these sites. You have an energy cost to put a second electron on the site. So you have a process where an electron can hop from here to there, and an electron can hop back. Now it could be the same electron, in which case nothing would change, or the up electron could go here, and the down electron could go back, thus taking us from picture 1 here to picture 3. So in other words, implicit in this insulator is a process which is called superexchange, which allows the orientation of the spins to change. Another way to say it is just that this insulator, before you do anything else, is apparently characterized by a log 2 degeneracy per site, because nobody tells you which way to put down these spins until you look at this sort of virtual processes. So there is a second energy scale in the insulator, which is traditionally referred to as J, and if you just do simple second order perturbation theory estimates, it's a hopping squared, matrix element squared divided by an energy denominator, so some sort of T squared over here. Question?
So there you've essentially got an insulator because you double the unit cell and you switch.
I haven't doubled, well, I mean, in here, in this way, I drew it, I doubled the unit cell, but nobody told you which way to put the spins down.
Sure, but are there cases where you get insulators, sort of Mott insulators, where you don't double the unit
Yes.
cell? And
Yes, yes. I mean, yes, let me come to that in a second, but yes. Again, just like with the band insulator, if you add a hole, then things can move. However, how this guy moves will depend on the other spins here. So the study of this situation raises a variety of deep theoretical questions. In particular, I argued to you, but I didn't really prove it, or show any real evidence, that if you make the repulsion large enough, you should get an insulator, right? So you may therefore ask the question, what happens as you vary the correlation strength? If this U parameter is 0, you obviously don't get an insulator at 1 per site. If this U parameter is infinite, it's sort of obvious that nothing can move. So what happens in between? There has to be some kind of transition. The second issue, which you raised, is that in the simple picture I said here, if you have 1 electron per site, that electron has a spin direction, and nobody told you which way the spins should point. Until you put this superexchange, which does tell the spins which way to point. So there's a question of both long and short range order of the local degrees of freedom characteristic of this insulating state, and how both of those things affect the physics of the transition and of the motion of holes. Okay, so that's a general outline. Now, data reveal a number of things which you would like to start interpreting in terms of this picture. The first is that there are many materials, for example, lanthanum titanate, which are insulating when band theory says they should be metallic. Now, it's generically true that at zero temperature, these insulating materials have some form of long-range order, which effectively changes the size of the unit cell in such a way that you get an even number of electrons per unit cell. Right? However, at least in some materials, there is reason to believe that, let's say, that order is not fundamental to the problem. Right? And there are two reasons for this. The first is that keeping the electron concentration fixed, if you raise the temperature just a little bit, the order goes away and the insulating behavior does not. Right? The second thing, which is sort of shown here, is that if you change the carrier concentration a little bit, the order goes away, but you see behavior as the carrier concentration is varied, which is indicative of an approach to a non-trivial insulating state. Right? And so I wanted to discuss that a little bit here. And this brings up several points, which are, to my mind, still not completely understood. All right. So this is data from this, the Mott review article for the specific heat coefficient of lanthanum titanate and yttrium titanate as you change lanthanum for strontium or yttrium for calcium. Now, the thing about lanthanum versus strontium and yttrium versus calcium is that they're both closed shell materials that give up electrons. But the electron counting is such that the charge on the strontium is one less than the charge on the lanthanum. So therefore, it's going to take away one electron from the system. Similarly, yttrium versus calcium. So if you make this substitution, what you do is you take electrons out of the conduction band. Well, out of somewhere, and the natural place for them to come is the conduction band. So roughly, lanthanum titanate is one electron per site. Strontium titanate, the titanium D band would be completely empty. There would be no electrons. In between, you get 1 minus X electrons. If you have lanthanum, 1 minus X, strontium X, titanium. All right. Now, let's look at, and here, this is a Hall effect measurement. And of course, the Hall effect is a can of worms. It is very difficult if you really take it seriously in detail to interpret it. But in common with many things in physics, and I think this is something that Pauli called the law of conservation of sloppiness, a naive interpretation, in fact, works quite well. And you know the naive classical interpretation of the Hall effect is it's 1 over the number of carriers. So if you interpret the Hall effect as a carrier number, then you get this curve here. All right, which gives you the number of carriers versus X. And you can see that the number of carriers basically is linear in X. All right, so this doping is sort of doing what you think it is, at least, if you want to think in a naive way about this material. Okay, so now let's look at the specific heat. This solid line is what you would get from somebody's band structure calculation. The specific heat coefficient is 0 at this end because you got no electrons. As you fill up the band, it just goes up to something because you're getting more. Now what you see is that as you get down in X below 0.5, the measured specific heat takes off rapidly upwards from this theoretical calculation. So just like in the helium-3 case I showed you before, you see an electronic mass enhancement. And as you see, all these things have a non-zero Hall coefficient. If you look at the resistivity, they're metallic. So everywhere in here, you have a metal with a renormalized mass, renormalized relative to the band structure calculation. And the renormalization diverges as you go towards the insulator. You get a similar renormalization if you look at the magnetic susceptibility. So the black things are the specific heat coefficient, the open circles are the susceptibility, and they're both blowing up. So like in the specific heat case, the idea is that at low temperatures you have a Fermi liquid. The entropy in this Fermi liquid, because the specific heat is just the derivative of the entropy, is enhanced, and the reason it's enhanced is that this Fermi liquid comes from something which at higher temperatures is more or less a collection of disordered spins. So you start with, roughly speaking, log 2 times 1 minus x per site. You can think of each site just as having a spin. Motion of the carriers correlates the spin on a very low scale and quenches the entropy and gives you a specific heat. It's very useful, I should have put it on the view graphs, to have this picture in the back of your mind, or in the front of your mind. So if I just plot entropy in a very naive picture versus temperature, at high temperature I have approximately free spins, so I would have an entropy of log 2 per conduction band electron. Right? Now we say that there is some scale below which the entropy is quenched. And we know that at 0 temperature you should get a unique ground state, so the entropy should be 0. So you have a curve which is sort of like that. And so the scale here of the slope has to be something like this. So spin entropy at high temperatures quenched into an enhanced mass. And it's obvious that as you lower the temperature scale at which your entropy is quenched, you increase the low temperature specific heat coefficient. All right.
The non-attraction curve is 1/3. How does it rise for gamma? How does it rise with
You mean down here?
yeah?
It's whatever the Fermi liquid result is. It's m star kf, and n is kf cubed, so it should be 1/3. To be honest, the main thing is that actually the band structure here is a little bit tricky because what you really have is 3 interpenetrating 2D bands, which then get a 3D character because of hybridization only at a very low scale. So your actual 1/3 is right here, and it's more close to just a step, which is what you expect in 2 dimensions. That's a quirk of this band structure. And to be honest, I would bet you that the calculations were done at a few points and in some plotting program interpolated. So I wouldn't take the shape too carefully. The main thing you should take away is this difference. So at some dopings you have a modest mass enhancement, at some dopings a much bigger one. Now, all right, so therefore you get a mass enhancement which has the characteristic dependence on number of carriers measured relative to half dome. Right, and that's the other sort of phenomenological answer to your question. None of this is magnetic or otherwise ordered in this range. So this precursor effect, therefore, is believed to be a precursor effect of something approaching a Mott insulating state with no particularly strong local correlations. Exactly how strong the local correlations are is a question of current research. Right? And you'll notice that the thing I was trying to sell you was that basically the properties of a doped Mott insulator should scale with the number of carriers. So if the spins are correlated by the number of holes in the Mott insulator, you should get that this TF is sort of like 1 over the number of holes, so you should expect a 1 over x divergence. And this definitely has more structure. And indeed, in the yttrium titanate, it doesn't even seem to be tied to x equals 0. So those facts still really remain to be understood. Okay, now, in answer to part of your question about the one-orbital Hubbard model, again, this reminds me of the parent whose child was not selected to be on the football team, and the parent says to the boy, well, don't worry, son, there's more to life than football. There's hockey in the winter and baseball in the spring. And sort of in that spirit, I want to say that there's more to life than this one-orbital Hubbard model. Right? In particular, first, and I should say actually I forgot to put the picture here, our qualitative phenomenological understanding of this really comes from John Goodenough and Kanamori. First, I've been talking about, let's say, D levels in transition metal oxides, which are localized. As you all know, in free space there are 5 degenerate D levels. In a solid, of course, you don't have a continuous O3 rotation. It's broken so the degeneracy is lifted, but it's not necessarily fully lifted. I should say, by the way, that although the term you see all the time is crystal field, in fact, the thing which lifts the degeneracy is hybridization. If you just work out the electrostatic potential of any acting on any d orbital in any reasonable solid environment, you will discover that the level splitting is negligible. It's all comes from hybridization. Okay, so in particular, if you have and that's the term ligand field means breaking of symmetry coming from hybridization to other orbitals. Okay, so in particular, if you have something in a cubic environment, like lanthanum titanate, you take your 5D levels and you split them into a 3 and a 2. If you lower the symmetry more, then you split these guys more. But it's quite common to find transition metal sites which have a point symmetry, which has enough, a point group which has enough symmetry that the orbitals you care about are in fact in A multiplied. So in the lanthanum titanium oxide, basically the point symmetry is cubic and the electrons are in T2G orbitals. So you need at least to say not just that there's one orbital on the site, but more than one orbital.
And can I just ask, so
Yeah.
when you say ligand or the hybridization, it's of D to some other band? That's what you
Well,
mean?
some other nearby atom, yeah.
Well,
For example, oxygen and lanthanum titanium all three.
uh-huh.
So it's the hybridization between the titanium D and the oxygen D. But really, more generally, it's the hybridization effect which splits all the levels, and not the electrostatic effect, right? And it's an elementary exercise you can do if you just sit down with point charges and say that, you know, the separation between a transition metal and an oxygen and a transition metal oxide is 2 angstroms. You can very easily work out how big this crystal field is just from E squared over R, and it's very small. Okay, so hybridization to oxygen is crucial. That's this little picture. So that in fact, the way electrons get from a transition metal, Tm here, to another transition metal is in fact not by direct overlap of these orbitals because they're too small. It goes via the intervening stuff, whatever the intervening stuff is. So these bands, I picked out this calculation which is done with a project I'm doing with James Rondinelli at Argonne, just because I happen to have it. There are techniques in band structure which are so-called fat bands, where what you do is you take the bands you calculate and then you project them onto different atoms using some algorithm which has a number of arbitrary parts that I'm not going to go into. But very loosely, at both atoms and orbitals. So, and then you represent the degree of overlap with particular orbitals by colors. So here, red, basically, the thickness of the red line here says how much, in this case, nickel, d 3z squared minus r squared, or dx squared minus y squared character it has. And the blue is how much d xy, xz, or yz character the orbital has. So if you look at the zone center, which is here, everything is basically pure because of the point symmetry. As you go out in the zone, they get somewhat mixed, but not that much, right? So what I want you to see here is that these two bands are the x squared minus y squared and 3z squared minus r squared antibonding combination with oxygen. These guys are the bonding combination. Similarly, this is dxy, antibonding combination with oxygen, and this is dxy, bonding combination. So all the orbitals in real life are mixed up to a not negligible degree.
So the scale is electron volt on that?
This scale is energy electron volts, and this is some tour through the Brillouin zone. I'm sorry I suppressed these points. So that's just what I said here. And very roughly, the way crystal fields work is that the EG orbitals hybridize much stronger with the oxygen than the T2Gs. So you get EG bonding and anti-bonding, which are split by a lot, and the T2Gs sit in the middle. And then you can discuss where you want to put the Fermi level. So in lanthanum titanate, basically the Fermi level is here. The EG antibonding is negligible, is essentially not occupied. In the nicolates, the T2G antibonding, as you see, is essentially full, and the action is in the EG antibonding. Okay, now going back to orbital degeneracy. So once you have more than one orbital, you have two things. First, you have different possibilities because different orbitals have different physical shapes, so they talk differently to their neighbors. But second, you have more interactions which are possible. If you just have one orbital, you can put 0, 1, or 2 electrons. If you have 0 or 1, there's nothing to interact with. If you put 2, it's in a singlet state, so there's just one parameter, which is the energy of putting 2. Once you have more then you have a more complicated family of interactions. All right? Now, in fact, the nice discussion of this goes back to the 1950s, at least for atoms in free space. The good book is this one, which actually comes in several volumes. All right? And basically, what you should say is that, an atom is a complicated multi-electron interacting system. So if I have a d orbital, for example, an atom which has a partially filled d orbital, even if I can forget about the other orbitals, I should label the eigenstates of the d orbital by their quantum numbers. All right, and there's a quantum number which is the total number of electrons in the orbital. There's quantum numbers associated with the total spin, and quantum numbers associated with the total angular momentum. So you get an energy which depends on many quantum numbers, and therefore you need many parameters in order to describe this energy. Right? Now, that's of course true from a fundamental perspective, but if you actually want to do any calculations or even have a reasonable conversation with someone about what happens if you put these atoms in a solid, you need to go down from a general description in terms of eigenstates to a basis, a representation in terms of single particle orbitals. All right? So the basic idea, which again goes back to Slater if not before, is you choose a basis. For example, your favorite d orbitals, dxy, xz, yz, d3z squared minus r squared, dx squared minus y squared. And then you devise a Hamiltonian whose eigenstates give you these energies. You can do this exactly for an isolated atom. If you want to talk about an atom in a solid, then you have to start asking what is the relevant range of energies where you do this. All right. So here's an example. Again, if you just take a usual angular momentum basis for the d orbitals, you have some radial wave function, you have the thing which gives you d symmetry. All right. And then you get some general Hamiltonian, which so then you have quantum numbers in this single particle basis, which are m and sigma if you force everybody to be in angular momentum, d with angular momentum 2. So you have these labels, and you have an interaction which, in general, connects all these different labels. All right? And what you should do is take this general interaction and choose these things to fit the exact eigenstates of these quantum numbers, or compute them. So the way you do that is you take, this thing is really defined in terms of the overlap of these wave functions this way. You just take the matrix elements of E squared over R with your favorite wave functions. Right? So I sort of sketched that here. Okay? Now, so in general, this is a complicated interaction which has many parameters. In fact, if I counted correctly, 85. Of course, in symmetric situations, for example, an atom in free space, these things simplify substantially, and you can express these in terms of interactions basically just between multiples of the charge density. Right? So there's a crucial parameter, which Slater called F0, which is just what you think of naively as the Hubbard U. It's the density-density interaction, if you like the charge-charge or monopole-monopole interaction. Right? So it's just E squared over R with the charge density with the charge density squared. Then you can define F2, which is a dipole-dipole interaction, F4, which is a quadrupole-quadrupole interaction. If you have materials where spin-orbit coupling is important, then you have to worry about the mixing. Then you really want to talk about J states and not LM states, and you need additional parameters which are called G, which I'm not going to go into. All right? Now, for d orbitals, if you're willing to neglect spin-orbit coupling, then in fact the only non-zero parameters are this F0, F2, and F4. And furthermore, for d orbitals in free space, if you're dealing with just the lowest d symmetry state, there's a definite relation between F2 and F4. F4 is some multiple of F2. So there's really only two parameters, right? Which in conventional notation are referred to as U and J. All right? And then choosing this occupation number basis, you can write all of the energetics, which reproduces just exactly diagonalizing this Hamiltonian with all these integrals, in this form, in this particular basis. So there's a U term times a thing which looks like the Hubbard interaction for each orbital, something else times U minus 2J with this, U minus 3J times this, and various other things. So if you add up all these things, there are 85 interaction terms which are determined by two parameters. Right? And this is the kind of Hamiltonian you should really treat if you want to discuss orbitally degenerate situations. right? And you're willing to focus only on on-site interactions, right? This thing, which in practice is widely used in calculations in solid state physics, is really inherited from symmetries of the free space wave function. If you go to lower symmetry, you break this relation, you break, because you don't have perfect rotation symmetry, you can't express everything just in terms of simple multiples, and you in principle start to get more and more parameters. So it looks quite complicated. There is one simplification which is worth bearing in mind. Basically, the structure of all of these interactions in the solid state is that there are two things. One is the monopole interaction, this F0, which basically just is the charging energy of the atom. It says, how expensive is it to change the total number of electrons on the atom? Then there's all the other interactions, 84 in this d orbital case, which pertain to how do you arrange, how does the energy depend at fixed number of electrons on how you arrange the atoms or the electrons in the orbitals on the atom, right? So those are loosely J. And the complication in solid state physics is that basically you get more J-like parameters, right? So there's always a U which is big, which is the basic charging energy, and then one or many, quote, J parameters, which say at given fixed charge, how do you arrange the rest of the guys?
So this J, how big is it usually compared to crystal fields or?
Well, crystal fields, of course, vary a lot.
For D,
With-
for D.
No, but I mean, again, crystal fields, of course, depend a lot on precisely the crystal structure, all right? So a better way to say it is as follows. There's, and in fact, let me see, is it here? This is to make the difference. Let me see if I can find here. No. All right, so it's in a different, it's in the next talk somewhere, so we'll go back to, all right, so, for atoms in the gas phase, where everything is very simple, rule of thumb is that J is 2/3 of an electron volt per pair of spins.
Can you say it again? Sorry.
Yes, the rule of thumb for atoms in the gas phase is that J is 2/3 of an electron volt if you view the J as a pairwise interaction between pairs of spins. So of course, if you have a high spin state, you know, your actual energies are J s squared or J s times s plus 1. But
J
roughly,
is the Hund's,
yeah.
whatever you call it.
But so roughly 2/3 of an electron volt per pair of spins. The U's, if you really take the physical size of a d orbital, which is this half an angstrom and so on, and you don't worry about screening, are 15 to 20 electron volts. Okay. However, yes, Patrick? Okay. Yeah, right. However, screening is important. So in the gas phase, the U's are 15 to 20 electron volts, which again, you can estimate that order of magnitude just from E squared over R and the fact that a d orbital is half an angstrom big. All right. But I said to you that this F0 parameter is the monopole-monopole interaction. In other words, it's really the charging energy of the atom. Okay. So the U parameter compares putting n electrons on and the energy cost of putting n to putting n plus 1. Now, of course, if you're in a solid, if you change the charge, right, that changes the electric monopole field coming out from this, and all the other degrees of freedom in the solid will react to this and screen it, right? So the 20 eV number, which you would get in the gas phase here, is not relevant to most solids, because all the other degrees of freedom in the solid will do something if you really make a local charge change here of plus 1, right? And exactly what they do is a question of current research, but a good rule of thumb is that it cuts it down by a factor of 4 or more. So the numbers you should have in your head are U's of a couple of eV, and J's of the order of 2/3 of an eV.
Sorry, I'm in this, psychological difficulty right now. One thing is to put, effective single particle Hamiltonian being screened by something else, but now you take interaction as being screened by this by the interaction.
Okay, very good. I'm sorry. This is something which I should have perhaps said, but here, if I just take this interaction for the moment, you can see if you just go through the algebra that you can rearrange this to so this is the charging energy, and this is at fixed charge how you arrange everybody in the universe. Right? So if you're willing to take this, then essentially the definition of U is energy of the system with n plus 1 particles plus energy of the system with n minus 1 particles minus twice the energy of the system with n particles. So if you just have a black box that gives you energies for some fixed charges, right? This is the question you should ask of your black box to find out what is this U parameter. In other words, it's just a discrete second derivative, right? Okay. But once you view it this way, then it's very natural. If you just make a thought experiment in a solid, you take your starting ground state. Now, I change that state by taking one electron from here and putting it there, right? Then I can ask, how much does the energy of my total solid change? And by moving an electron from one site to another, I have made electric fields now coming out from each site. And the rest of the solid is going to react to those electric fields. Right? So that's why.
I understand how screening works.
Yeah, but that's why. But that means that there is a screening contribution precisely to this energy difference. Right?
I think
Yeah.
the question is that now you're going to solve this many body problem, and then you're going to do more screening.
No. This is
So
what.
I think if you were trying to say that this screening is from the other electrons,
Yes.
you would integrate it out.
Correct.
So
Again,
it's
this
from
screening.
different electrons, then it's different.
Correct.
If it's from
This
four
screening.
electrons or whatever.
Right. This screening is from the additional electrons, and I said that this was a topic of current research. Right. For two reasons. First, your treatment of all the other electrons is basically band theory plus more or less perturbation, and you can argue about whether that's good or not. Right. But second. In many cases, if you go back to my little picture here, right, untangling other electrons from the electrons you care about is not necessarily a trivial procedure, right? These things are transition metal oxygen hybrids. So people are still fighting about what's the best way to do that untangling. But conceptually, it's screening just from the other electrons. Really view this as a thing sitting in some kind of dielectric medium and ask if you change the charge here, how does that medium polarize? So conceptually, it's screening from all the other electrons, knocks the U down substantially.
Well, I'm only saying that
Yeah.
if I look at free electron gas, right?
Right.
And I have this E squared over
Right.
interaction, it would be incorrect to put screened interaction in the Hamiltonian.
Correct.
Right. But
Although, actually, let's go back because it would, at least you have to be careful how you do it. The entire GW approach to band structure is precisely that. And there are intelligent ways of incorporating the RPA resummation in step one.
Right.
But that's a separate topic that I'm not going to go into.
Okay.
But for here, just for a simple-minded way of thinking about it, to discuss the correlated features we want to abstract out of the solid some particular set of electrons that we care about. And the U is screened by all the other electrons that we haven't included in the set we're studying.
Okay.
All right? And I'll show you a picture, I think I won't get to it till tomorrow, which is obtained from these RPA-like calculations, where you can see that quite most of the screening really comes from stuff which is very far away. And the arguments have to do with whether you're talking about, when you get down to the level of is the screen U 2 or 3 or 5, then you really have to face up to how you disentangle this into the orbitals you care about and the orbitals you don't care about. But what gets you from 20 to a number of order 5 is states which are down here and states which are up there. Right. So again, the rule of thumb is U's of the order of a few eV, which are screened strongly, J's of the order of 2/3 of an eV per particle pair, which are screened only very weakly because what J is measuring is the changes in energy as you put guys in different orbitals, keeping the total charge fixed. So what J corresponds to is quadrupole and octupole fields, which of course are affected by the presence of a solid, but much, much less strongly than the monopole field. So you get, 10%, 20% renormalizations of J for these calculations.
Right, thanks.
Okay. Patrick?
No, I'm used to thinking of J as an exchange.
Right.
Constant, but you describe it as a multiple, so.
So there's two different things. I'm not sure there is. So the first statement is that when you do these computations, and this really goes back to Heisenberg and Hund, the energy comes from averaging higher multiple combinations of these things over an orbital. The on-side J here.
I mean, I can interpret the exchange integral as a multiple.
Yeah, as a Coulomb interaction between higher multiples. It's the part which isn't the monopole. Look at it that way. I mean, so if I go back to this general expression here, right? There's one part which is just the monopole-monopole interaction, and J is everything else, right? And you would agree that J is not this, whatever it is, therefore this has to come, if in particular, if you have no spin-orbit coupling, it's all,
No, it's within the.
yeah, it's within the shell and it has to be higher monopoles.
But physically, it's correct for me to think of it as an exchange.
Yeah, in fact, the big term comes from the Pauli blocking of some configurations and not others, right? I mean, that's the reason for Hind's first rule. It's just, if you put everybody in the same spin state, then the wave functions are automatically farther apart.
That's really good exchange.
Yeah, and then there's a second term, when the second rule says after you maximize S squared, then you want to maximize L squared. And that has a more transparent interpretation in terms of multiples, right?
What is that?
So, well, because angular momentum is, states of different angular momentum precisely correspond to, I mean, you can discuss it without knowing anything about spin, and it precisely corresponds to just, it precisely corresponds to the multiple energies because that's what relates to states of higher angular momentum, right? Angular momentum 0 is the monopole. So where did it go? Here, right? So it's this, just Hund's first rule says after you fix n, Hund's first rule says maximize s, and Hund's second rule says after you maximize s, maximize l. And all these things come from doing integrals here, which are mathematically nothing but different
Why
multiples
is it
of charges.
maximize L?
Oh, it's the same reason that if you maximize L, you're making the wave functions be physically farther apart. All right, so let's go back. This stuff now makes a difference. And this is jumping ahead a little bit because I haven't really told you about metal insulator transitions, and here I'm telling you that it makes a difference to something I haven't told you about. All right? But this is work that Philip Werner did quite recently, because it's really only in recent years, thanks to the stuff that Philip did, that we can actually do calculations within various approximations for these kind of models with all of these complicated interactions. All right. So this is a phase diagram as a function of chemical potential, which you can think of as particle number, and interaction strength for a model of 3 orbitals. And all I want you to point out is that all I want you to see is that what's inside here, here, and here are insulating phases. Right? And everywhere else is a metal, except to the left of here, which is insulating because there's no electrons. Right? So there's an insulating phase with 1 electron, an insulating phase with 2, an insulating phase with 3. Right? This red line is the critical U you would get if you just took the same density of states and you had only a 1 orbital model. Right? So therefore, orbital degeneracy makes a difference to the metal insulator phase diagram. Not a qualitative difference, but a quantitative difference, which is not necessarily small.
I missed what you said.
Yeah.
If you just did one band model?
This would be the critical U to get a metal insulator transition at n equals 1. And I don't have a picture in this plane of chemical potential and U for the 1-band model.
These examination?
No, this is dynamical mean field theory.
No.
All of these.
No, this result.
All of this result is dynamical mean field theory, single-side dynamical mean field theory for these models. Both this one and that one. So, for a semicircular density of states. So the only point here, I'm not trying to say that any of these results are the exact answer. I'm just trying to say that the orbital dependence does make a difference.
Is there some general rule, like if you increase the number of flavors sort of your electrons, then something happens, or?
Yeah, although, I mean, there are a lot of general rules which were derived by approximate analytical methods and which I don't think are quite right. And to be honest, we haven't really gone back to this and condensed it into some general rules. There's some obvious things you can see here. More orbitals does make it harder to be insulated. The difference is not very much if you only have one electron in these three orbitals. It's much more if you have three. So this is just orbital degeneracy. You can now add this J, again in this free space rotationally invariant form, and you see quite pronounced changes. The chemical potential scale is all screwed up, so, well, let's say is substantially modified. But you turn on a relatively modest J, which is just some fraction of U, and now what happens? The one electron thing becomes much harder to make insulating. 2 becomes much easier. 3 becomes easier again. Right? Now again, this is fairly easy to understand. If you go back to the 3 electron case, what having a non-zero J does is it says you want to be in a high spin state. Right? So if you have 3 electrons and 3 orbitals, you put them in a high spin state, you filled up all the orbitals. The next electron has to go in with the wrong spin. Right? And so it feels, if you like, an extra energy cost, which is its J interaction with each of the 3 electrons that's already there. Right? So that, if you like, substantially increases the effective U, and therefore pulls down where the transition is.
Andy,
Yeah.
can you explain what's going on with the 0? I mean, I can, the 1, 2, and 3 is probably each of the orbitals opening a gap.
Wait, no. Sorry. This axis is chemical potential. I
Right.
said this too fast
Sure.
before. So this is the insulating state with a mean electron, with an electron density of 1 electron per site. This is the insulating state with 2 electrons per site. This is the insulating state with 3 electrons per site. So as you increase chemical potential, you have 0 electrons, totally empty band. N changes from 0 to 1. Right? Then you have an insulating state with a gap, so there's a non-zero range of chemical potential where it stays 1, then it goes from 1 to 2, insulating state with 2, 2 to 3, insulating state with 3. So that's the meaning of these numbers.
That's the Coulomb blockade plateau.
Yeah, it's exactly Coulomb blockade plateaus, which, as you see, are strongly affected by this J. But yes, as I tried to remark before, that all the physics of this really is, if you like, Coulomb blockade in a solid state context. Yes?
In comparison to the size of changes you get by doing multi-bands and J's and U's, what's the size of change of this if I just choose my bands differently, or I build up my sort of original bands?
Well, I guess,
The bands in a
well, you
different
see,
way?
always the problem is compared to what?
Well, compared to, right?
No, but I mean, the point is, once you have a different band with some shape, then I need a metric, right? So within this class of calculations, it's actually a fairly robust result that if you just take a 1 orbital model with some not entirely unnatural density of states, the critical U is 1.5 times the bandwidth. So if I just fix everything to be constant bandwidth, as you change densities of shapes, in my experience, you tend to get 5, 10, 15% changes in critical U's at fixed bandwidth. You can do, of course, some highly unnatural things where if you go from a band like this to a band like that, right, then it would be different because your bandwidth is really,
But I'm just
Yes.
asking if I make reasonable
Yeah,
choices that are
right.
slightly different.
yeah, no, reasonable choices that are slightly different seem to move things around by 10%, 15%. With one subtlety that I'll get back to. Next point. In fact, the open symbols here are what happens to this lobe if I increase J. Now suppose that I go away from having complete orbital degeneracy. This was a model with 3 orbitals which were all degenerate. In other words, there was a cubic point group symmetry, if you like, in this calculation. If I break that degeneracy to make 1 go down and 2 go up, you see the metal insulator critical point changes quite substantially. Actually, I think we did this. This is 2 down and 1 up. That's why the 2 state changes a lot. Right? So the position of these phase boundaries is very dependent on J, on the orbital degeneracy, and on even relatively small liftings of the orbital degeneracy. Right. So this is really all just to say that these things are important and make a difference. Right? And in fact, again, I don't want to go into details, but this paper by Pavarini and others, basically argues that if you take your best guess at what is the interaction strength in lanthanum tightening, so it in fact would not be insulated if all the orbitals were degenerate. And in fact, if you look carefully at the actual crystal structure, which is not cubic, but a little bit different from cubic, it lifts the orbital degeneracy by an amount which is relatively small, but gives you a shift like this, only a bit bigger, and actually is what makes that thing insulated. Okay, so multiple orbitals, their degeneracy and how it's lifted is clearly a crucial aspect to all of the physics, right? And I think that that has been well established by now, but let's say specifics beyond that are not yet well understood. So for example, people have not gone from this qualitative argument of Pavarini and company back to, for example, a coherent account of the specific heat coefficient versus doping curve that I showed you before. It's clear that that extra structure must be connected to these phenomena in some way, but in what way is not yet understood, at least not to my knowledge. Okay, second example that you should have in your head. I'm going to choose the example of high temperature superconductors, although it's far from the only one. These are a canonical example of, quote, Mott insulators. The electron counting is that you have 1 electron per unit cell at 0 doping. These things are insulators. When you dope away from the, so you see that here, this is frequency-dependent conductivity. You see a gap which is between 1 and 2 eV at x equals 0. As you add carriers, you clearly build up states inside the gap. So more or less doped Mott insulator with a variety of interesting phases associated with that. However, these things really are not quite Mott insulators. Going back to sort of basic chemistry, these are made up of a transition metal and oxygen. The oxygen is very electronegative. So you put oxygen in a compound and it basically sucks up 2 electrons to complete its p shell. And that has an interesting interaction with the rest of the electronic structure. So here is a naive picture of the electronic configuration of lanthanum cuprate and of this lanthanum titanate material I showed you before. Copper is a so-called late transition metal oxide, meaning its D shell is almost full. And basically in lanthanum cuprate, you have 1 hole in the D shell and a filled oxygen P shell. In lanthanum titanate, you have 1 electron in the D shell and a filled oxygen P shell. All right. Now, suppose I want to add a hole. I want to take out an electron from here. All right? Basically, the local energetics are such. In lanthanum titanate, it's implicit in everything I said. You just take the hole out of the D level. So you go from D1 P6 to D0 P6. Of course, these bands are all hybridized and so on, but this is still a reasonable starting picture. The energetics are rather different in lanthanum cuprate and in the other late transition metal materials. If you take out a hole, it's much cheaper to take it out of the oxygen than to take it out of the copper. So basically, if you do 1 hole removal from this material, it takes you from D9 P6 to D9 P5. Right? Here's the same thing again, in slightly different pictures. Right? I argued for you here that the effective U was starting from a system with taking 2 atoms with some number n of electrons and moving an electron from one atom to another, so I go from 2dn to dn minus 1, dn plus 1. That's not the only process. If you go back to late transition metal oxides, then the process is, in fact, take the hole off the oxygen. Right? So here's an energy diagram which sort of shows that. Here we have our starting thing with copper D9. If I want to go to copper D8 in the high TC materials, that costs a large amount of energy. It's the first place to put a pole is here. If I want to add an electron, the P's are already full, so I have no choice but to go to D10. So in the jargon of the field, there is a thing called the charge transfer gap, which is the difference in energy between the copper level and the oxygen level, which is delta. There's a charging energy U on the copper site. And in the late transition metal atoms, the delta, I have this inequality wrong, the U is big compared to the delta. So therefore, the cheap process is the one which involves delta. Right? In other words, the charge transfer process is cheaper than the double occupancy process. All right. So therefore, the high TC materials are properly regarded as charge transfer insulators. And to understand their properties, you really have to involve this other orbital in an essential way. All right. This classification was introduced by Zanen, Zawadzki, and Allen in an important paper in 1985. They basically said you classify materials as Mott, Hubbard, or charge transfer insulators according to whether the charging energy U is bigger or smaller than the energy to simply put an electron on another orbital. And so an important question is, for materials, is where do you put materials on this general phase diagram? And more generally, you could say this brings up the issue of covalency between the correlated orbital and the other orbitals. Right? And finally, a question you might ask is, given all this, what difference does it actually make to the low energy properties that you care about? And these questions, I think, are still subjects of active research. Okay, so this charge transfer insulator thing highlights the importance, at least in some circumstances, of other orbitals, which don't necessarily have strong correlations on them, but which are important to the physics. There's a last class of materials that I wanted to discuss in my sort of botanical survey, which is a more extreme example of the importance of other orbitals, and that is the so-called heavy fermion compounds. All right, so here's an example. These are alloys of a thing with a partially filled F shell, for example, cerium and other stuff. Right? Here's an example of specific heat data from a heavy fermion material. As you come down, this is specific heat divided by temperature plotted versus temperature squared. At high temperatures, what you see is a straight line. This is just the phonon contribution to the specific heat. As you may know, if you just have normal electrons, although there is a specific heat term which is linear in temperature, its magnitude is such, because the electron mass is light, its magnitude is such that you can't, it's very hard to distinguish from the phonons until you get to very low temperatures. So this is the usual phonon T cubed. You see that as you go to low temperature, the specific heat coefficient turns up. Here's a blow up, specific heat coefficient versus temperature on a linear scale from very low temperature up to 1.5 degrees. You see that the specific heat in units of millijoules per mole Kelvin squared is about 1,000 and is constant. Right? If you translate that into effective into mass numbers, this is a constant specific heat coefficient, so it looks like electrons. The mass you would infer from this value is something like 1,000 times the electron mass. Hence the term heavy fermions. Now, it was actually conceptually very important, I think, for the development of the field that these materials, in common with helium-3 and various other things, are not only strongly correlated Fermi liquids, they have instabilities to other interesting states, in particular superconducting ones. The reason why this is important is that at the superconducting phase transition, as you know, there's a jump in the specific heat, which is related to the gap or the transition temperature and the underlying specific heat of the electrons. So it was found out, I think by Steglich, that the specific heat jump at the superconducting transition of this guy, which happens at about 0.5 Kelvin, is basically the same size as this. So whatever the entities are which are giving you this enormous mass are experimentally sufficiently like electrons that they can go superconducting. Right? So this, I think, is what really convinced people that you have here really a heavy Fermi liquid, because whatever the entities are that give you a heavy mass participate in the superconducting transition. Right? Yeah?
If you just fit this through BCS theory, the local.
That's in fact this jump. That's this solid line is the BCS using that. Now, of course, these are D-wave or some other kind of complicated superconductors, so as you start to go down here, it's different. Also, there aren't enough materials difficulties that, you have to accept in your mind some broadening. It doesn't get a lot better than this, really. But roughly speaking, it is BCS with the specific heat corresponding to the heavy mass. So these really are heavy fermions. Okay, so what's going on here? Basically, in all this class of materials, these things give you wide conduction bands, right, and a basically metallic state. This thing here, the f orbital, is extremely localized. And at high temperatures, it just acts like a magnetic moment. Here's a plot of the inverse susceptibility. This here is more or less a Curie by stir. right? So at high temperatures, what these things look like is basically free spins, which is the one electron, let's say, living in the F shell, and a wide conduction band. At low temperatures, somehow these two entities get married and become a heavy Fermi liquid, right? So you can study this by formulating a lattice version of the Anderson model that I showed you the last time. And the interpretation of the physics of these compounds is that the heavy fermion state is some sort of lattice version of this Kondo resonance, which I showed you last time in the context of the single impurity Anderson model. The fact that the hybridization between these levels is very weak means that if you go back to my picture here, this is the picture that obtains at room temperature and down to some quite small temperature. This scale is maybe only 10 Kelvin or something. So the large specific heat comes because you quench the entropy of the local moments on a scale which is in practice remarkably low. All right. So again, in this case, to understand the physics of these materials, somehow the entanglement between the orbitals which are correlated and some other bands of uncorrelated orbitals is crucial. Okay? So, to summarize what I've told you in this qualitative survey is that first, there are many things about both helium-3 and materials that you want to understand. Even if in many cases the ground state of a metallic system is Fermi liquid-like, you would like to understand the physics at scales above the Fermi liquid scale, the nature of the instabilities to other phases, and the origin and properties of metal insulator transitions. You want to relate this to the local structure of orbitals and atoms in the crystal. And to do this, the things that you have to deal with are strong local interactions that involve multiple quantum numbers, not just a local repulsion. All right? So that's the basic thing, the basic problem that one has to deal with. And in the next lecture, I'll get your question in a sec. Basically what I want to sketch is a set of theoretical developments which are at least one way to get at this class of questions. So, question.
So is it the target of all of this to come up with a generalized Hans-Rule?
I guess I'm not sure that I understand the question, but probably not. I mean, I would put it slightly differently, in fact. The target is really that, let me put it this way. Hund's rule and its generalizations are basically statements about this term in the interaction. So roughly speaking, if I have a localized system with a conserved quantum number, which is the total number of electrons, right, and some orbitals, then I can discuss at fixed number of electrons, how do I want to arrange those fixed number of electrons in the orbitals I have. That's really the question that Hund's rule is addressing. And clearly, as you go away from the simple picture of an atom in free space, you have to generalize the simple rules that you had before, because the quantum numbers are not the quantum numbers of the atoms in free space. Okay? But for the purpose of the discussion here, I would like to say that that's background information that you should just do. And it is basically doable because this is just finite system quantum mechanics. All of the strong correlation physics concerns how this, whatever it is, interacts with the fact that the number is not conserved. So that either electrons can hop from one correlated site to another, they can go from the correlated site to other bands in the solid. So it's the interplay between this local physics and the, let's say, K-space nature of wave functions that we normally think about when solving, the Coulomb-Sham equation. That is the essence of the difficulty. What you really have to do is marry the local physics, which is transparent in its own domain, to the itinerant physics, which is also transparent in its own domain. It's putting those two things together that is the essential difficulty.
So intra-orbital interactions are transparent.
Well, yeah, I mean,
So
yes, but it's because it's finite system quantum mechanics. Once you have some modest number of orbitals, 5, 7 or something, and some interactions, you have a matrix. It could have 500 entries, it could have 1,000 entries, but it's just a matrix you can deal with. So that's the sense in which I mean it's transparent. But once the total number is not conserved, then you really have a quantum field theory of some sort to deal with. In the back, yeah.
So, back to this, Mott transition. Somehow you mostly speak about single particle quantities. That mass being large, getting large,
Yes.
becoming large,
Yes,
or
yes.
probably z getting small. What happens to actually collective modes?
What a good question. Basically, that's not something which is well understood, and it is an object of current research. In a sense, the focus on single particle quantities is very analogous to the old joke about the drunk looking for his keys under the lamppost. Right? It's a set of questions that we know we can address and that give answers. There is clearly things happening to collective excitations, simply because, as I sketched for you, the basic Mott insulating state, right, which is characterized, if you like, by an odd number of is characterized by each site having some number of degrees of freedom, which in the naive Mott picture are simply uncorrelated. So in other words, the naive Mott state has an extensive entropy. Nobody tells you what spin to put on each site. In more complicated models, nobody tells you exactly which orbital to occupy, right? So clearly there is physics which will quench that extensive entropy, all right? And exactly how that interacts with the various phenomena that we're talking about is still a subject of research, I would say. Right? So it's a non-trivial problem. Yeah.
So you've written down sort of a model of homospongy and
Yeah.
essentially said if I ramp up the number of bands, I sort of get closer to the real
Correct.
material properties.
Yeah.
Is there any other sort of way one can interpolate between really getting the real material answer and sort of these models other than just increasing the number of bands?
Well, it's actually worse than that. I would say that increasing the number of bands is not really the problem. I mean, in some sense, effective field theory or effective models are the right way to think about things, right? And I would imagine that it's very reasonable to integrate out things which are outside of some energy range, right? And then you're dealing with, deep filled orbitals, high up empty orbitals are only going to have a small effect. The basic weakness that I perceive with the model systems. So just to go back, I think although it hasn't been investigated in that much detail yet, as you expand your energy window, the interesting properties that you care about, metal versus insulator, ordering temperatures and so on, will converge reasonably well as a function of window. The big difficulty, which I'm going to mention briefly tomorrow, is this focus on local interactions. There are lots of phenomenological reasons to say that this is the most important thing. And a lot of the way we think about it is really guided by our experience with helium-3, where it's the only thing, right? But it's clear there's a long-range Coulomb interaction. There are interactions between the correlated orbitals and the things I'm literally talking about as uncorrelated. It's putting those in an intelligent way, which it seems to me is not yet understood. And so it's really how much you want to expand your space of interactions is where I see room for more thought, at least. Yeah, Leo?
Yes, I have a question about, so it seems like there's really two energy scales. One energy scale is the hybridization energy between the itinerant and the moment, that
Yes.
moment. And the other is, this TF star of the eventual heavy fermion
Yeah.
that we get. And somehow here there's this, you're saying the entropy starts getting quenched.
Well, wait. Let me just go. Can we discuss your question more precisely in terms of this?
Right.
Okay. So I would say it's slightly different. In this simple, let's say in simple approximate theories of this model, all right? Basically, the physics we care about, this U is very large, it's not really a scale. So the important scale is this.
Right, so that means
Okay.
we're reducing F to spin, basically.
Well,
Spin.
no, because U is large means we don't have F2, but we still have F0 and F1.
Okay.
So it's not precisely space. But, so I would say that this TF star is a function which theory can determine of this. There's a whole separate story, which I don't want to go into here, why TF star is a much smaller number than this. I mean, this is basically the fact that the Kondo effect is logarithmic. But in this simple way of thinking, this TF star is basically just a function of this V. You make V bigger, T star gets bigger, there's some relation between them we can discuss, but there's really only one scale. The question, which is implicit in things which various people have asked, is there additional physics beyond this sort of single-site picture? Is there another ingredient just than the value just of this V star which goes into this TF? Right? Is there a parameter which has to do with collective modes, with intersite spin exchange, something like that, which also helps control this? And that's again a subject that people are fighting about now.
Okay, but what is the index F on TF?
Oh, then I just meant it to be like an effective Fermi temperature. So if you like, going back to my field free picture, if I look here, right, I have an effective heavy Fermi liquid, which is characterized by some Fermi temperature, which is, if you like, just the inverse of the specific heat. So that's all I mean is this.
But I guess that's what I'm not understanding. So why can I not have another scale
Oh, you can. And that's a subject of current research.
above TF star, where, so if I'm at that intermediate,
so
temperature,
basically-
I'm not degenerate.
Yeah,
These
here,
Californians are not degenerate.
so if I may just say, basically, here I've given you a sketch which only has one scale. There's one thing that happens. You either have free spins, they get quenched by just one thing, so, and then you get one specific heat, right? So what you're really asking is, why couldn't I have something like this with some other physics in here, right? And that's a very reasonable question. And indeed, there are clearly materials that do this. And I would say that it's not yet understood exactly why. Right? But this thing with one scale is the simplest possible picture. And again, just going back to this, I guess this is the simplest possible picture, and it's a very good thing to have in your head as you think about these problems. But as Leo says, real life is certainly allowed to be more complicated.
But you say experimentally in both cases?
Yeah. And in fact, experimentally, there are not only both cases, but there's a larger number of ambiguous cases where people are quarreling to this day about whether you should think about it this way or this way. Right. And this comes back to, I mean, just, I should stop shortly, but where I'm going next time is basically dynamical mean field theory, which focuses really on local interactions and local physics. And so the kind of thing it gives you is this. Right? And therefore, almost by definition, this sort of thing is non-local physics, which is not well encoded in the approaches that I'm going to tell you about. And getting a reasonable formulation to do honest calculations that encode that is really the big open problem. All right, so is there other questions, or shall we break for lunch at this point? All right, looks like no more questions, so we'll stop here. Thanks very much.